Let me start by thanking the organizers, especially Yenting, for the invitation and opportunity to come to Taipei for the third time. And more importantly, coming to this conference gave me impetus to go back to work on galaxy clusters, which there was been a hiatus for the last few years. I was working on something else, and so I'm back with galaxy clusters. So what I'm going to talk about today is basically mass bias in cluster cosmology, and especially related to Planck clusters. So it's very specific, it's broad, it's basically led by a former postdoc of mine, who was also actually a graduate student of mine, Asif, who is now in France, and also a young master's student. He's looking for a PhD position now. Okay. And for people who don't know me, everyone, almost other than a couple of people, most people don't know me over here. So I come from TI for Mumbai, and so if you guys are in Mumbai, please feel free to send me an email and you can visit us. Okay. So since there are many master students over here, I would do a brief introduction before I move on to the main topic. And there are a few slides over here which I will skip through, but they're still there in the talk so that people can look at it later. Okay, so let's do this as cluster counts. Oops. In a nutshell, so remember the count, when you say we'll do cluster cosmology, and there have been two great review talks over here by Brad and Inon about SZ and X-ray cluster cosmology, where they detect number of clusters and have this fantastic cosmological results. What you do is basically detect these clusters in a cosmological sample as a function of redshift, which comes from follow-up. And for SZ, there is some signal to noise ratio. For X-ray, there can be some count rate, and compared to theoretical number counts. So this is the theoretical prediction of cluster counts. And over here, this is the mass function times volume element, which has all the cosmology in it. And we detect a cluster over some signal to noise ratio, and this probability tells you what is the probability mean inside out of a cluster of given a mass at some redshift s. So this is something which is very important. This tells us whether we have actually detected that cluster or not, and how will we detect. Now this mean probability, this is actually connected to the mean as a signal. So I'm talking about Planck of the cluster at mass m and redshift. And this thing to mass, this comes from the scaling relation. And of course, there is a mass bias, which is going to be the focus of this talk. Now, there is also a noise over which these clusters are detected. And the noise detection is by a filter at the cluster's position. And because we want to detect SZ in a fixed aperture, which is typically the R500 or theta 500, so you have a scaling relation which basically connects these two. Now to break the size flux degeneracy, so to ensure that the SZ signal is extracted from R500, we again have to look at the mass of the cluster and know what is the R500 of the cluster. And given the redshift of the cluster, we know what is theta 500. And so there is a theta 500 to mass scaling relation coming over here. And this is what Planck in general uses. Okay, typically what people used to use before. This M, for example, over here, remember, this is not the real mass. It is the hydrostatic mass supported only by thermal pressure. So in this formula, okay. Now the cluster masses have non-thermal pressure, which people have talked about before. There was a very interesting talk by Naomi, the first talk today. And so this mass must be converted to the real mass of the cluster, which should incorporate the non-thermal pressure. So a quick slide of non-thermal pressure. This non-thermal pressure comes from bulk motions and turbulence in the intercluster medium. Now we have a formula. I don't have the formula over here. And we have seen from hydrodynamic simulations from like last 20 years that every cluster has non-thermal pressure, and the fraction of this non-thermal pressure sort of increases with radius. So it goes higher and higher as you go to the real radius of the cluster. And at any fixed radius, the non-thermal pressure fraction can be large, basically, for larger clusters. So two things, it increases with radius, and for larger masses, it's larger, which is what simulations tell us. Of course, the first talk gave us something different, so I don't know what's going on over there. Maybe we have to change everything. Now, in because it's massive clusters, these are dynamically younger on average and more recent mergers, strong accident shocks, so there's turbulence. It does not come to hydrostatic equilibrium. But in contrast, smaller systems, groups are more relaxed and less non-convolution. Okay. So this was the relation that I showed before, but this was this hydrostatic mass. If I have to correct for this non-thermal pressure, which tells you that this mass is less than the real mass, then this is how it is done. So over here, this hydrostatic mass is actually replaced by the real mass of the cluster, this M500, by a mass bias 1 minus B. So if this is 80%, then 1 minus B will be 0.8. Okay. So the idea is we must get 1 minus B. And because since the number of clusters detected is a strong function of the detecting mass limit, so if I have a little difference, like 20% difference over here, that makes a lot of predicted difference in the number of clusters, so you're going to get completely wrong cosmology. That's the simple idea. Okay. So let's see how we try to do that. Now, so this is the sort of infamous 1 minus B. In the first Planck papers 13, they first did it with basically no 1 minus B term. Their cosmology was very different from the Planck same cosmology. Then they introduced 1 minus B term. And what they did was they introduced a constant 1 minus B term. So how you do it? You look at the hydrostatic masses. So in Planck, they look at 62 clusters. And for some of those clusters, 37 clusters from the Canadian Cluster Cosmology Project was there. So they had recleansing masses. So they basically had a 1 minus B, a constant 1 minus B of 0.78. Initially there was 0.8, they later changed it to 0.78. But even with this, the Planck cluster cosmology sigma 8 does not match with the Planck CMB, primary CMB sigma 8. So there is a difference. So primary CMB sigma 8 is higher. Okay. Recently, like almost 10 years of the Planck results, there has been renewed interest, and there have been a few papers coming about. For example, there is a paper by Emmerich et al. In last year and this year, which has many people from the Planck cluster cosmology team actually in the paper, where they do this 1 minus B a little more carefully. They have a larger 160 clusters with Chandra analysis, hydrostatic masses, and 93 from the DES year 3 recleansing. And over here, instead of having a constant 1 minus B, they have a mass dependence and a Z dependence. They try to basically marginalize these parameters along with the cluster numbers to get these numbers. Okay. And what they find is that if we have a constant 1 minus B, then this is the number. And if I have a mass dependence, let's forget about the redshift dependence right now, then this is the number. Okay. So one thing that sort of troubles me a bit is that if I look over here, this alpha is positive, which basically means that the higher masses have less bias. So higher masses, the hydrostatic masses are close to the total masses. But simulations over the ages would tell me that for the higher masses, the hydrostatic masses are actually less than the drop. So it should go the opposite way around. Now, what's there, I don't know. But one of the interesting things is that if the alpha is there and the alpha is the way that it is, then what happens is that in the cosmology, so this is the Planck cosmology paper. So this is from the Planck paper. So you can see a high sigma 8 from the primary cosmology, which is slightly higher than 8, sigma 8. These are the cluster numbers with different thresholds. And now, recently, they reanalyzed it. If you have the one where you have a 1 minus B of 0.85, or another one where the 1 minus B was with a mass dependence. First of all, let's look at the sigma 8 over here. See it yourself. So, first of all, as you can see, if you look at the green plot, this is 0.77. So, it's, as we know, it was still not the same as Planck. But with this mass dependence, when the mass bias increases with higher masses, decreases with higher masses, you go for the smaller. So you begin away from Planck sigma 8. And in fact, if you have redshift dependence over there, you go even more away from Planck sigma 8. So that's what they have. Okay, so now, what is the reason? I don't know. The reason maybe there is a recleansing mass calibration, something is going on over here, or maybe there is also some hydrostatic masses that will be also different. So the other thing is that we can do galaxy clusters in computers. So this is what we want to do. So I always spend like most of my time, so I'll go very quickly. So we looked at clusters in the 300 project. So yesterday there was a talk which showed that the 300 projects actually has a large number of clusters. Of course, its baryonic resolution is low, but you don't need to have too much baryonic resolution because you don't care about the center of the clusters. Okay? And we identified 3 samples of galaxy clusters at these 3 redshifts. We have a total of 1,655 clusters. And the masses of these clusters are very similar to the blank masses. Okay? Now, if I quickly just look at the total mass M500 and the hydrostatic masses of these clusters, then this is the result, which is not one-to-one. So obviously the hydrostatic masses is less, okay, for both relaxed and unrelaxed clusters. And you can have some relation with this, which is what traditionally one does. The point to be noted over here is that to do this hydrostatic masses, we really need information at one point. We do not need the whole profile. So the mass at M500 hydrostatic just depends on the pressure at M500 and the density at M500. Okay, you have to of course go up to M500, but you don't need to have information about the profile. Now that basically means that we are sort of not using a lot of the information. So what we want to do is do a machine calibration to this and try to see if we can get this bias better. So this is a graph neural network. There is a poster outside which basically tells you very nicely for a different topic what is a graph neural network is. So you can go and look over there. I don't have time, but basically it trains your model with simulation data and then tries to predict it. You have something which is there also. Okay. So I'm going to go very fast. If you want to read about it, there are 3 pages over here. I told you what it is. So I'm going to skip this. This is what we want to do. Okay. So now with this machine learning, let's see what we can do. So we have this number of clusters. We divide it into a training sample and a testing sample. So the training sample is basically 9,000 clusters. Testing sample is 1,050 clusters. It's made from these clusters by putting in different redshifts. Okay. And in the training sample, you see this is the training set. This is the true mass, and this is the mass we recover, M500. If I know, the very important thing, if I know the density profiles of the gas and the temperature profile of the gas. So this is exactly how the Planck people had normalized. They have basically extra observations, they know the density profile, they know the temperature profiles, and from there they do hydrostatic mass. So I know the density and temperature profiles. Here's the whole profile information. It's a very good reconstruction. It has basically 6% dispersion. And then if I do it on the testing, so the things that we don't know, we almost get the same back. So it's a very, very good way of doing it. Okay, so now if I look at real cluster data, they go up to R500, sometimes they go a little less than R500, so we can basically test that. There are many more plots in the figure. So if you go a little less than R500, change the number of bins, we really do not change much until we go to very, very small radial bins. So if you're really not probing much and trying to extrapolate, so going like 0.3 of R500 or 1, then of course our results are not very good. Otherwise, if we are probing density profiles up to closer to R500, then the reconstructed masses are excellent. So then we can look at the reconstructed masses and the hydrostatic masses. So this magenta is reconstructed, and then the hydrostatic masses are this. Sorry, it's the same sand, it's yellow, it's strange color over here. Anyway. And you can see something over here. This is a very interesting plot that if I have done from observations, this mass bias would have a much larger scatter, which is like 6 times bigger scatter than if you are doing from the machine learning. And the reason is that observations only looks at the one point, and anything which is going wrong in that one point can give a large scatter. Machine learning takes all the information from all the points up to there for the both temperature, the density, the gas mass fraction, everything. This is something that we can discuss tomorrow. So let me quickly go to the last plot. So finally, this is the mass bias. Once we train these things, we can actually go and look at exactly the clusters that the Planck people used to look at their scaling relations. These are the Rex's clusters, some, and some XCOP clusters. So basically these 2 clusters. The XCOP are the ones with these circles. The Rex's are the ones without the circles. And you see that over here, this would have been the true, if there was no mass bias, and this is actually there, so there's a mass bias over here. So this is the machine learning trained on the simulations used over here, and we get this mass bias like this. There's this beautiful trend. With higher masses, as you can see, more non-thermal pressure, more biased. And so this is the result over here. So this is different from what we got before. So there is a correct, I think this is the correct trend. So we'll basically are getting larger masses over here. So those are the rise direction in reconciling Planck cluster cosmology with the Planck theory. So a lot of details are there in this paper. If you want to read through it. So I'll stop over here, look at things that we are sort of doing right now. There are a lot of things that we can do, and we have sort of doing a few of these things. And I'm happy to take questions. Thank you.
Thank you so much. I didn't catch the maybe detail exactly, but so your sample you analyze is different from Planck cluster sample.
No. So first you train the set in the simulation samples to see that your training is good, and you train it exactly the way Planck would do their cluster analysis to get the hydrostatic masses, and so look at the density profile. So it's not like just total flux over mass, which we would have done. So you basically look at radial thinning. Now, there are some more details over there. Once you do that, and you know that if I know our density profile and know our temperature profile, know our gas mass profile, I know exactly what SM500 is. Now I can go back to the Planck clusters. This has now been done in the simulations. Now I can do in the real data with the XCOP and the Rexus clusters, which are the clusters they had. And there, now I can get their hydrostatic masses. I can get their total masses from this using the same replication. And then these masses go in their scaling relations, where the YSZ is what they measure. So that's what we did, and that gives it bias.
Yeah, sounds very interesting to apply that to also to checkmate.
Yeah.
Very deep Excel data. Okay, since time is limited, yeah, let's come have for the next talk. So the next speaker is Erwin Lau. We're going to talk about variant pasting.